So it is a pleasure to have Raúl González Molina with us today, who is going to be telling us about Futaki invariants and the Hull-Strominger system. So please.
Yeah, thank you for the introduction, and thank you for the opportunity to report on this progress. It's a recent work with my advisor, Mario García Fernández, which has to do with the existence problem for the Hull-Strominger system and to develop some tools to tackle this problem whenever. And as you cannot see in the front page, this will appear hopefully very soon in the archive. So yeah, the motivation was explained in Sebastian's nice talk yesterday, which has to do with rate fantasy. It's this proposal to connect different components of the modular Calavilla of threefolds into a single irreducible component through these surgeries in complex geometry that are called conical transitions. And as Yao proposed, the Hull-Strominger system should serve as a good geometrization for this problem. So let's start. My geometry will be a compact complex manifold with a holomorphic volume form. This is my definition of Calavilla manifold. Okay. For all purposes, you can think of a threefold, but most methods won't care about the dimension, and a pair of fixed holomorphic vector bundles over the manifold. Okay, so let me introduce what I understand as the Hull-Strominger system. This is a system that asks for a Hermitian metric on the manifold and a pair of Hermitian metrics on the bundles, and fix a positive real constant. And then we ask for this set of equations to hold. Just right away, you can see that the second equation is giving a balanced class, which I regard in bot-chain cohomology. Okay, and I stress that I will ask for my Hermitian metrics, for both Hermitian metrics, to be instantaneous. Okay, and sometimes in the literature you can find this first bundle to be, sorry, it's a little typo. There should be here a 0 and a 1. The first bundle is the tangent bundle, but our methods won't care about this. They can be whatever holomorphic vector bundles we want. Okay, so let me speak separately about each of the equations. The first one is the well-known Hermitian-Einstein equation, then by Donaldson-Yao theorem. We know that this is a stability condition with respect to these balances, right? So not for a Keller class, but a balanced class. Then the second one, apart from being a condition for a balanced class, it also tells us about some restriction on the complex topology of the manifold. Not every manifold admits this. And also it has a hidden holonomy condition. The bismuth connection for this metric will have reduced holonomy in the special unitary group. It's called conformally balanced. And then the third one, the most mysterious one, equation in the system is the so-called anomaly cancellation equation, or the Bianchi identity, heterotic. And we are going to see what is telling this equation for us for the geometry of the manifold. Then our question, the question along this talk is, which are the balanced classes that are reached by a solution to Hull-Strominger system? Okay, and our strategy will be, as I said, to geometrize to see what this equation tells us, and to study the geometry and topology of this gadget we are going to construct. So we take it easy and start with the pluriclosed case. This goes back to an old observation by Bismuth. So he asked for a metric, for a Hermitian metric on the manifold to be pluriclosed, which is what sometimes physicists call the large volume limit. Okay, so then I consider this smooth bundle, the tangent plus the cotangent, and a Dolbeau operator, which is not just the holomorphic tangent and the cotangent, but it's twisted by this term here. And of course, the pluriclosed condition amounts to saying that this operator is integrable. So this is a holomorphic vector bundle. And I choose the most naive metric that I can think of. So the metric and the inverse metric and the tangent and the cotangent. Okay, so the content of the observation is that if one identifies via the metric the holomorphic tangent with the anti-holomorphic tangent, then the chair connection of this data before corresponds to the Hull connection. Okay, so it's like the bismuth connection, but with a flip in the sign of the torsion. This connection here. Okay, so now let's try to generalize, not for pluriclosed, but for the for our setting, for the anomaly cancellation equation. So I'm going to stress in red what are the differences with the previous case. These are my unknowns, the metric in the manifold and the Hermitian metrics and the anomaly cancellation equation. Then we can add to the previous bundle a factor given by endomorphisms of the holomorphic vector bundles I fixed. Then I can choose some fancy terms here in the Dolbeau operator. And now the anomaly cancellation equation amounts to this new Dolbeau operator to be integrable. So this is again holomorphic. Okay, and here this term is inspired by the anomaly cancellation equation. Okay.
Sorry, Raúl.
Yeah.
You said NGI. You have only like one of the bundles?
No, they are the both. But I am considering at the same time. When I write BI, it means B0 and another term for B1.
So like the direct sum.
It's like endomorphisms of B0 plus endomorphisms of B1. So it is the bundle of split endomorphisms, right?
And there's no assumption that V1 or V2 is related to T.
To T. No, we don't care about that. It can in particular, but we don't demand this. Okay, so now this is our new metric with the pairing given by this expression, the bundles V0 and V1, or V1 and V2. And I warn that my metric will not be positive. So it's a pseudo-Hermitian metric, unless I choose to drop one of the bundles, precisely this one with the flipped sign. Okay. So now we try to mimic Bismuth's observation and use the musical endomorphism to identify this bundle with this one. It's the same thing, the same identification, and we get some new expression. One can check that if we drop the bundles, the terms having curvatures, etc., we recover Bismuth's observation. Okay, so it's a sign that we are on the right track. So now let me speak a bit about the generalized geometry in this situation. Then this bundle I have just constructed fits into the generalized geometry formalism. It is a current algebroid, holomorphic, but it is non-exact. Okay, so here in the projection, I don't have the tangent bundle. I have the Atiyah algebroid of the frame bundles that I chose. Okay, so I have this new factor coming from the endomorphisms of the holomorphic vector bundles, and the anchor is just the composition of these right maps. Okay. Now these admit a natural pairing and a bracket, and also the holomorphic structure is given by a procedure of reduction plus the axioms of the Jacobi identity for the bracket. This is a procedure that was first understood in a series of articles by Gualtieri and Burstein, Cavalcanti, and Gualtieri. And also, the rest of the structure is natural in the sense of generalized geometry. So this metric is produced just by the pairing and a choice of generalized metric. Okay. So I don't want to be too technical about this. I have to progress. But I will discuss the details afterwards.
Sorry, Raúl, you say it arises from T bar Q arises from reduction of what?
Yeah, so it's a procedure that was sketched by Gualtieri yesterday. It is a choice of a lifting in the complexification of a real string algebra, and then perform a symplectic reduction. We can speak of that afterwards. So the upshot is that generalized geometry is a formalism that permits to encode the solution, the information of a solution to the anomaly cancellation equation in a current algebroid, and we have a preferred metric, the chain connection, a preferred connection, that is the chain connection of the metric. Okay, so now I will assume that I am given a solution to the anomaly cancellation equation, and I consider this string algebra. And from now on, I will speak of holomorphic current algebroids, and I will assume I am referring only to this type of holomorphic current algebroids. Okay. So we can compute the metric properties of this pseudo-Hermitian metric. Here is the curvature tensor. There are some fancy operators arising. There are many things coming up. These are for example, the curvatures of the bundles, the Hull connection, the torsion here of the metric. This is expressed in terms of classical tensors.
I'm sorry. What is boldface at?
Yes, it's written here,
Would that define
evaluated on a vector and contracted on some, there is a quite complicated expression. Yeah.
Well, okay. Yeah, thank you.
Okay. So this is one of the main results we have reached. If we have a solution to the full Strominger system, so not just the anomaly cancellation equation, but the full system, then if we consider the associated holomorphic current algebroid with this metric, then this metric is in fact Hermitian-Yang, okay, pseudo-Hermitian. A few remarks about this result is that this is a...
Sorry, can I ask,
Yeah.
is this an if and only if?
No, it's just an implication. Okay, I'm going to comment on that. So this is an exact version of a theorem that was already known in the physics literature in this paper by Xenia de la Osa, Magdalena Lasfors, and Eric Swans, in which they study the G2 system in one dimension more and perform a reduction and see that the information of a solution to the Hull-Strominger system is in fact in all orders in perturbation theory to a suitable current algebra with a Hermitian-Einstein metric. In our context, as you were pointing, our results says the following. So this is true, but we have this result even in milder situations. So we don't need the full power of a solution to the Hull-Strominger system, but just the solution of a relaxed version one can ask for in any compact complex manifold just with vanishing first-chain class. So in particular, this will not be the topic, but we can speak afterwards. This is nevertheless makes links with several interesting topics such as flatness, generalized Ricci flatness for non-exact current algebra, generalized Ricci flow, and some supergravity equations on the physical side. Okay, and one more thing is that we computed this in by a standard geometric, like a standard differential geometric calculus, and we expect a generalized geometric proof of this fact, which we still don't know. Okay.
What do you mean? What does that look like? What you mean? I mean, you're connecting something generalized and classical. Like, well,
yeah, but I mean, our methods are not the generalized geometric ones. Like no mention to spin geometry. No, we just computed these terms you were asking for. Just classical differential geometry. You want. Okay. So now we are going to exploit this result of having a Hermitian-Einstein metric, and since this is a condition that has an interpretation of moment map equation, we can consider the associated Futaki. Okay, so this is a general machinery that comes whenever you have an equation with a moment map interpretation. So to explain what is it, let me begin with a very classical situation. So for a moment, forget about the geometry that I have talked about and just consider a compact complex manifold, a balanced class, and a holomorphic vector bundle, whichever it is. Okay, so then this map here that has the Hermitian-Einstein term, this defines a character in the Lie algebra of holomorphic endomorphisms, and this does not depend on the choice of even pseudo-Hermitian metric, so it does not depend even on the signature, and it does not depend on the representative of the balanced class. And what is obvious from this equation is that if we have a solution to the Hermitian-Einstein equation, then this term vanishes. Okay, this will be important afterwards. So then we now are going to enhance this Futaki invariant to our setting. And to do that, let me introduce a classification result by Garcia Fernandez, Albacino, Rubio, and Tiple that says the following thing. So if I go back to my geometry, so non-Carrera Villao and fixed holomorphic vector bundles, then there is a classifying space for the set of equivalence classes of holomorphic current algebras which extend the fixed holomorphic vector bundles. And this is, in fact, an affine space that is given by the image of this cohomological map. So the del operator in this cohomology space. Okay. Then we do the following. We are not going to consider a single Futaki invariant.
So what is 118?
It's a cohomology. Yes, by duality with Botchen cohomology, we have another complex cohomology with it, which I denote by H11. So over this classifying space of holomorphic current algebroids, we have a family which on each fiber, it is just the family of holomorphic endomorphisms of the holomorphic current algebroid. It is defined at each point of the classifying space. And then just our Futaki invariant is the evaluation at each fiber. So for each fiber, we have a different holomorphic current algebroid, and it's the Futaki invariant for that. And here we have written that it takes values in Apley cohomology just by duality integrating against any balanced class which lives in Botchen cohomology. Okay. So now the result is as follows. I've stated this as a theorem, but it's just a consequence of what I have said up to now. So if we have a Calabi-Yau manifold and holomorphic vector bundles, and we have the classifying space for the holomorphic current algebroids, then assume we have a solution to the Hull-Strominger system, then there must be some S in the classifying space, so there must be some holomorphic current algebroid such that its Futaki invariant vanishes, just because a solution to the Hull-Strominger produces some holomorphic current algebroid with a Hermitian Einstein measure. Okay, for pairing against the balance class of my solution. Of course, the point of all this is to use an obstruction. So we are going to reinterpret this invariant as an obstruction to detect the impossibility to find solutions to the Hull-Strominger system. Let me explain how this goes. So just a little definition. If we consider this geometry and a fixed holomorphic current algebroid that extends the holomorphic vector bundles, I will say that that solution to the Hull-Strominger system lives in this holomorphic current algebroid just if the associated construction, if the associated holomorphic current algebroid is isomorphic to the one I fixed. Okay, so it's just a method of classifying where different solutions to the Hull-Strominger system live. Then the result is as follows. If we have some fixed holomorphic current algebroid and some fixed balanced class, if my Futaki invariant doesn't vanish, then there's no way there's going to be a solution to the Hull-Strominger system within this current algebroid and this balanced class. It's just the reciprocal of the previous result. And now a more strengthened version is that in this geometry, suppose that I have a balanced class and that for any holomorphic current algebroid that I can construct extending the holomorphic vector bundles, I see that my Futaki invariant doesn't vanish for every element in the classifying space. Then there is no solution such that the metric lives in this balanced class. No solution whatsoever. And
can you just remind us where the Futaki invariant lives?
Yes, we have a full family of Futaki invariants. And for each point in the classifying space of current algebroids, so fix, for example, some holomorphic current algebroid, some S, then by this expression, this lives in Apley cohomology just by integrating against a balanced class by duality.
So for any endomorphism, you say that 118.
And in particular, if there are no global sections of,
then there's something to do with it, yes.
Automatically zero.
Yeah.
Sorry, like how should I think about this set of equivalence classes? Like, what is it coming from? Is it like this del omega?
Yes, there's this classification result. So you apply, del is an operator that is well defined at the level of cohomology, and you just take the elements in the image of this map. And this is an affine space for the classifying space is an affine space modeled on the vector space that is the image of this map. Okay. So
it's a vector bundle over an affine space?
No, it's an affine
classifying
space that is modeled on the image of this map.
So my question is, where does the Futaki invariant live? It's a point in what space?
So it's if you want a family of these applications.
Okay.
This is
So
just
it's a point in a vector bundle over an affine space, which you call H curve
yeah,
H?
yeah. Okay, but the vector bundle is trivial. Okay.
Okay.
So now what I was saying is that where was I think here. No. That was a little spoiler. Okay. Is it here? Yeah, sorry, I lost myself. I think I was here. Yeah, okay. So now I was saying that if I am able to choose a balanced class such that for any holomorphic current algebroid, this Futaki invariant doesn't vanish, then there is no solution such that the metric defines the balanced class that I chose. And I stress that the conclusion of this theorem is entirely classical and has nothing to do with holomorphic current algebroids. Just if I am able to compute all Futaki invariants for all holomorphic current algebroids. Okay, so in principle, this might be very difficult, but there's one particular nice example in which my manifold satisfies the delta bar lemma, algebraic manifolds, for example. Then the classifying space reduces to just a point, and then the family of Futaki invariants reduces to a single Futaki invariant. Okay, and this should be regarded as a higher Futaki, as a stringy version of the classical Futaki invariant, which does not obstruct a Hermitian Einstein metric on a bundle, but the full Strominger system. Okay. And this, of course, we hopefully this has some select implications in the geometry of race fantasy, because the proposal is to make solutions to the Hull-Strominger system pass across these conical transitions. But we start to see that if this kind of obstructions pop up, this procedure may not come for free. So, of course, the upshot is not that race fantasy must be false. It's just that this has to be meticulously done, because what has been up to now regarded as a Calavilla web in which I can perform these conical transitions may start to build some walls, and I have more kind of a labyrinth in which I have to travel very carefully in order to avoid these kind of obstructions. Okay. So now I just wanted to show you what is really boils down to computing this Futaki invariant. So here in this expression, in terms of classical tensors, a holomorphic endomorphism of a current algebroid is given in terms of this tuple, where phi is a section of the endomorphisms of the manifold. Sigma is a orthogonal section of the endomorphisms of the holomorphic vector bundles with respect to the trace pairing. AI are zero forms in this bundle. And B is just a 2-0. So it is just to give you a glimpse of what is really about computing this Futaki invariant. It can be quite complicated. Okay. Nevertheless, we have been able to compute it for a homogeneous geometry. Okay, in which case it boils down to linear algebra, which can be performed with a mathematical software. Okay, so the geometry goes as follows. We have chosen some Lie algebras in the classification of nilpotent real Lie algebras which admit a complex structure, and nil manifolds over them. So they are the isomorphism type of the Lie algebra together with a complex structure is equivalent to a set of structure equations for a spanning set of just the 1-0 part of the table of the Lie algebra. And then what I said, the geometry is to choose the associated group and quotient by a discrete compact lattice, so we get a homogeneous compact manifold. Okay, and it has a very nice projection to the standard for torus. These geometries were already considered, in fact, to produce solutions to the Hull-Strominger system by Fernandez, Ivanov, Ugarte, and Villacampa. Our approach here is opposite. So we try to obstruct the existence of solutions. So here we consider an easy SU3 structure given by a balanced metric in terms of these homogeneous, these invariant tensors. It's a balanced metric, and this is a holomorphic volume form, and it gives right away a balance class, which I included, the standard balance class of this geometry. Then I choose as my bundles possibly the most easy example, which is to drop one of the bundles and to choose the other to be a line bundle, which comes from the base, from the tools. And then this line bundle is identified via its curvature. Okay, so via its turn curvature. We have some parameters here that determine the topology of the line. Then we have an easy solution to the anomaly cancellation equation for some string parameter that I don't really care about, is bigger than 0, okay? And this produces a holomorphic current algebroid, which is my main object of interest. So the proposition goes as follows. If we have this manifold and consider the classifying space of holomorphic current algebroids extending this vector bundle I chose, then we have two results. The first one is that the classification space, this vector space, has dimension 4. But nevertheless, for any point which is different from 0, the associated current algebroid does not vanish against the standard balance class. Yes, so this invariant is non-zero, and as a consequence, we know that for any other current algebroid that is not the one produced by this solution, then this does not support a solution to the Hull-Strominger system in the standard balance class. It is that this can be omega 0 and h0 is the solution to the full system. So there's no way we are going to obstruct this. So, but for the current algebra is different from this one. This successfully captures the impossibility to find a solution. So yeah, the result is this. So for any holomorphic current algebra that extends this line bundle I chose, then we either find a solution or we find an obstruction. Nice. So on the minutes I have left, I want to comment on some new perspective of the Hull-Strominger system, which have to do with stability.
So just before you do,
yeah,
do you have a solution with V0 being the holomorphic tangent bundle and V1 being non-trivial?
Not for the moment.
Or obstruction?
No, yes, we are still working on this kind of examples. We still don't have that. We'll carry. So yeah, then in this part of the talk, I will assume that I have a solution to the Hull-Strominger system, and I consider the holomorphic current algebra associated. Okay. So recall that the metric I constructed is not positive. Okay, unless I drop one of the bundles. So I cannot speak of slope stability, at least in the most classical sense, because just the tolerance theorems only applies for positive metrics. Okay. So in fact, we have this result. So we assume that our manifold is Keller-Calavilla, okay, and we have a solution to the Hull-Strominger system. Suppose further that the balance class associated to my solution is the square of a Keller class. In this situation, then the associated and I suppose that I can use a standard slope stability. So if I assume that my holomorphic current algebra is polystable with respect to this class, then I have a rigidity result, namely that the metric of my solution is Keller and the Hermitian metrics are flat. So if I want to speak about non-Keller solutions to the Hull-Strominger system, this is a hint that is a standard slope stability for holomorphic current algebroids may not be the right notion, because these kind of rigid things happen. So we need to find somehow a differentiated notion of stability for holomorphic current algebroids. This is what we are going to do next, but the picture is mostly conjectural for now. So I assume a solution for the Hull-Strominger system and consider the associated holomorphic current algebroids. And now my guideline principle will be the theory of Higgs bundles, loosely. So given a positive Hermitian metric, so G is not positive, but I assume given a positive one, H, then we have two associated decompositions. Firstly, we can consider the Hermitian and skew Hermitian part of the connection. And secondly, I can choose the Chern connection of H, and a remaining piece I will call in analogy the Higgs field. Okay, but the warning is that in this setting, the Higgs field is most of times not holomorphic. This is an important difference. Okay, then the Hermitian-Einstein equation associated to a solution to the Hull-Strominger system in the current algebra has an associated Hitchin equations under this decomposition. Okay, and now in the Higgs bundle theory, the Hitchin system is a system that is associated to a hyperkeller moment map set of equations, but unfortunately ours doesn't. So we choose to complement it with a condition on a positive Hermitian metric, which we call harmonic condition, in order to have a hyperkeller moment map picture. Okay, so this begs the question if this can always be done. So if I have a solution to the Hull-Strominger system and consider the associated holomorphic current algebra, does it always carry a harmonic metric? We still don't know. This is an open question, but on some examples we have found it just does, and it just does by a very easy argument which has to do with flipping the sign of a term in G just to make it positive. Theoretically, we still don't know if such a holomorphic current algebra always carries harmonic metric. Yeah.
What is the connection acting over there? What does that say? J?
Yeah, psi is a
Psi,
one
I
form
understand
that.
What is the J?
J is the complex structure on the manifold, and it's extension to one forms and there's also a complex structure on that.
And Q value.
Yeah.
I see.
And
is that
endomorphisms of Q values.
Oh, yeah.
Yeah.
And is that equation like variational?
Variational.
I mean, how did you choose this? Does it come from Lagrange?
Yeah, this comes in order to complement it with the Hitchin equations we have found associated to a decomposition in order to have a full system which has a moment map interpretation.
It's a hyperkeller moment map.
I see. Oh, yeah. That's what you said. Okay.
Yeah. So we have no answer for the moment for this question, but supposing we had a harmonic metric, then we can propose a sensible notion of JT stability, one that seems to work for the moment. And how does it work? Okay, so let me consider a holomorphic vector bundle which has a pairing and a connection, just in the case of holomorphic current algebras in the setting, such that these conditions happen. So the 0-1 part of the connection recovers the holomorphic structure, and such that the Hermitian-Yang-Mills for this connection is satisfied. Then I will say that this orthogonal holomorphic vector bundle is semi-stable with respect to this balance class if for any coherent subshift, which is isotropic with respect to the pairing, and that is this is the key part, which is preserved by this connection. If these conditions are satisfied, then the slope in the classical sense is less than or equal to 0. 0 is just because an orthogonal holomorphic vector bundle must be slope 0. This is the definition for semi-stability, a proposal for semi-stability, and then stability and polystability are defined in a similar manner.
Sorry, what is D?
D is a connection that I have in the data, and I ask that this connection has 0-1 part recovering the holomorphic structure and is Hermitian-Yang-Mills with respect to some balanced elementary.
So that means that the stability condition is not purely holomorphic?
And what do you mean?
You're asking for it to be depreserved. You're asking for it to be preserved by a unitary connection.
It's not unitary.
No,
it's pseudo-harmonic.
it's a complex connection.
Is it a holomorphic connection?
You ask if this is integrable. Yeah.
It's not holomorphic.
No.
But anyway, here's the result. In this geometry, non-Keller Calabi-Yau in general, and for fixed holomorphic vector bundles, if I have a solution to the Hull-Strominger system, and supposing the associated holomorphic current algebra carries a harmonic metric, then we have the easy implication in the Kobayashi-Hitchin correspondence. Then Q must be polystable with respect to the balance class given by the solution. Of course, we still don't have the harmonic.
Is this condition of I mean, what Marco was asking, I'm also puzzled by that, the preserve. Can that sort of interpret in terms of the heating equations that you were?
Yes. In fact,
So maybe there it makes more sense.
it is actually equivalent to being preserved by my non-holomorphic Higgs field, but it's just easier to consider to be preserved by the connection than to be preserved with respect to a Higgs field you obtain from some mysterious harmonic metric.
Yeah,
But it's actually equivalent.
But is it, should I be worried about the fact that a stability condition is not purely holomorphic?
I don't know what should you worry about.
It's just usually the stability condition is a condition in algebraic or in complex geometry, not in Hermitian geometry. Right. Usually you have a holomorphic condition that guarantees the existence of Hermitian metrics of a certain type or connections of a certain type. So I mean, you may be right.
It's easy to check.
You need to be open-minded here. So even for the result that Jeff and Josh were talking about the other day, the stability condition depends on the metric for bismuth harmonic, and this is something very tricky. Everything is coupled.
Okay.
Everything is coupled. So it's new.
Okay, so I just want to make sure that it is strange. Okay.
That's open-minded, but then probably GIT maybe closes your mind a little bit because
this is mostly connected.
We're not saying that this is a GIT stability condition. It's just that
there's some stability conditions.
So be preserved means on the open subset where it is actually countable.
Yes, that's it. For a general coherent subshift, I have some subset outside which is the sections of a vector band.
So what's your opinion about the condition for any isotropic involutive subsheet? We have this condition. If that was the condition, it would make a lot more sense.
with respect to the bracket.
Yeah, with respect to the bracket.
Yeah, the thing is we don't know how to relate the bracket with the connection. That's if we were, that would be amazing, and that would be ideally the thing.
Yeah, we have been trying to relate both things, but for the moment we still don't know how to go about that. Anyway, we have an easy direction of the Hitchin-Kobayashi correspondence, and it may be not the right Hitchin-Kobayashi full result, but nevertheless, we may use it as a further obstruction in a more algebraic sense than just using a Futaki invariant. So I just wanted to comment on some future directions for this work. We have evaluated the Futaki invariant, but just for not just, but our best results up to now are in homogeneous geometries. Of course, we want to apply it to the rates program. So the next thing to do is to evaluate it on an algebraic Calabi-Yau threefold, so the real thing. Of course, our results in the Hitchin-Kobayashi program ask for a harmonic metric. We still don't know if this is the case. So have to get some theoretical results that assure that a holomorphic current algebra carries a harmonic metric. It supports a solution to the Hull-Strominger system. And one last wishful thing is that in the same way that in the Higgs bundle theory, different incarnations of the Higgs moduli have essentially different complex structure, and they complot to give a full hyperkähler construction. Maybe different incarnations of the Hull-Strominger system, moduli of solutions and moduli of holomorphic current algebroids can interact in a very interesting way to produce moduli with strong structure. Yeah, and that's it. Thank you very much.
Comments or questions for Raúl?
Is the harmonic metric condition elliptic?
I don't know about that. Do you know?
Yes. The hyperkähler code
Should be, yeah, it should be.
And what about like uniqueness? Should it mean Okay.
For the moment, we just have it fulfilled on examples, but we haven't performed any theoretical analysis. Sorry?
The examples.
In the examples, we don't even know about that. We just have some answers.
Write one down.
Yeah, if you remember the Hermitian metric at the start of the talk, it had some minus sign in one of the components. Our answer is just to flip the sign and consider the positive Hermitian metric just by flipping that sign. And it appears to be harmonic in some geometries.
But not always. You know, it's not always.
Yeah, we don't have any argument to assure that this is always the case.
No, right. But is there an example where you're sure that it is not?
Yeah. We have the conditions for that ansatz to be a harmonic metric, and it's obviously not always satisfied. Of course,
Necessary answer. It still seems like you're not quite.
yeah, it's sufficient. It's sufficient,
Right.
but it needn't be the right harmonic metric to consider.
I guess this was asked before somehow, but this harmonistic condition, like usually there is an energy function. This is a, minimizing something. So
Yeah.
is there a function? Yeah.
Okay, that's a good suggestion.
Well, this is, I think, what Jeff was asking.
No, yeah, but go earlier. But yeah.
Yeah, that's, I mean,
It should be,
It's a good
at the moment,
direction.
Michael Kaler.
Well, for you, it's just
a hope.
Sorry. It just comes from like sort of aiming at this moment.
I take the suggestion as the natural thing to consider.
More questions?
Yeah, when you evaluate the Futaki invariant, it doesn't make sense to look at, I don't know, something, I mean, the balanced class, can it generate something singular, or is it possible, or it doesn't happen? I have no idea how balanced classes behave.
Yeah, in fact, we have evaluated without requiring that the metric is positive. So for any element in 2-2 Bot-Chern cohomology, and it produces a result. So it can be evaluated without the assumption that it is given really by a metric. So it is really a balanced class. And we have abstractions, but the thing is that then the system is abstracted with a conformally balanced condition that does not make sense. That it's not geometrical, but yeah, it's abstracted.
Okay.
Nonetheless, yeah.
So it's stronger.
No more comments I see, so let's thank Raúl again.